Hello everyone, and welcome back to the channel. Today we are diving into the world of x86 protected mode, the gateway from the 16-bit era into the modern computing environment we know today. We will explore how we can switch the CPU from a real mode to protected mode, set up our own GDT and IDT, run a custom interrupt handler, and yes, we will talk about how all of this ties directly into security, including attack paths and defenses. Let's start with a quick comparison. In 16-bit real mode, the CPU can only address 1 megabyte for memory. It relies heavily on BIOS interrupts for I/O, and there's basically no real oscillation or protection. Now, comparing the 32-bit protected mode, 4 gigabytes of address space, bit registers, hardware enforced privilege levels, and proper memory protection is completely different ballgame. To make this jump, we need two key data structures. The first one is global descriptor table, GDT, and the interrupt descriptor table, IDT. The GDT tells the CPU how segments map to memory, code, date, stack, all defined here. The IDT tells the CPU where to go when an interrupt occurs, whether that's a keyboard press, a timer tick, or a software interrupt like int 0x80. Both of these tables are loaded into special hidden registers inside the CPU. GDTR for the GDT and IDTR for the IDT, and we load them using LGDT and LIDT instructions. Here is how switch works. We load our GDT into GDTR. We set a PE bit in the CR0 control register, and then we do a fast jump into our new code segment. This flushes the instruction pipeline, reloads segment registers, and places the CPU into 62-bit protected mode. From here on, we have got access to all 62-bit registers, 4 gigabytes addressing, and most importantly, the ability to define our own memory protection rules. Once we are in protected mode, we can set up IDT. In my example, I have assigned interrupt vector 0x30 to a custom handler. When I trigger int 0x30, the CPU looks up that entry in the IDT, fetches the handler's address, and jumps straight into my code. No BIOS, no operating system inference, just a raw CPU control. Here is a live run. First, you see message IDT setup, then int 0x30 triggered in red. The handler executed and print handler in green. Finally, we hit done stopped in blue. That's our complete interrupt cycle, entirely under our own control. Now let's connect this to security. If an attacker can modify the IDT this early in the boot process, they can hook critical interrupts like int 0x80 on Linux to hijack system calls before the OS even loads. In real mode, that isn't as dangerous because 16-bit code can't directly run in project mode. But in project mode and even in modern 64-bit long mode, the same technique applies. That's why this stage of a boot process is one of the most contested areas in modern computer security. So today, we have gone from a real mode into protect mode, build our own GDT and IDT, and run a customer interrupt handler, all before any operating system was loaded. In next video, we will take this even further, loading an OS kernel and exploring more advanced control, both for defense and for offense. Thank you for watching, and see you next time.